Okay, so last class we were interested in explaining why we see in a very simple phase diagram for a simple fluid, as I've shown in this graph here, why does it behave this way? And actually, why is something that we really can't answer. I mean, it is what it is, right? That's nature. But we can perhaps ask, how does thermodynamics, one of the pillars of our current understanding of modern science, uh, uh, how does that explain what we see in reality? So if we think we know something, then we should be able to predict it. And so if we have faith in thermodynamics and its power, then it should allow us to predict, at least qualitatively, what we see in nature. Okay, and so that's the power of science. And one of the powers is that it allows us to predict things. And of course, this is why we can predict things like lunar eclipses and solar eclipses and where satellites will be and all of that. And so if you think, if people ask you what good is science, well, then, those are things that are obvious responses, because you need GPS on your phones. Otherwise, it's so easy to take a phone and take it for granted that I can get directions to anywhere on this planet. Uh, but again, that's just Newtonian mechanics and some relativity. Anyway, I can go on and on, but we'll stop there. So let me get back to the point here, which is explaining this PT phase diagram. And so this is a single component phase diagram that I've shown in this box. And last class, we saw that by an analysis of the expression for dg, which we know now is, the molar Gibbs free energy for pure fluid at constant pressure, because you see here that this green arrow in the boxed figure is going across at constant pressure, is really telling us that the molar Gibbs free energy, or the chemical potential of a pure system, is determined by entropy, so, or at least the rate of change of that chemical potential as a function of temperature. The constant pressure is related to the entropy of the phase. And through an analysis of looking at the various entropies, and then connecting that to the slope of the chemical potential as a function of temperature, we saw that this plot is something that we can qualitatively arrive at. Okay, and so the nature of these curves, which are telling you the slopes, okay, are indicating or suggesting slopes of mu versus t for a pure fluid. They're just qualitative. Okay? They can be rather complex in general, but for illustrative purposes, we can think about these as simply linear functions, but they're definitely not linear in reality. But even with the simplistic analysis, we see that based on the variation of mu versus t, and connecting that variation and its slope through the entropies, we see that we can recover the phases and the phase transitions that we see in a phase diagram for a single fluid. Okay, and so it all arises from the fact that chemical potential is minimized at any given combination of temperature and pressure. And so if the system has a choice between solid, liquid, and vapor, it's going to choose the phase at a particular combination of temperature and pressure that's going to have the lowest chemical potential, i.e. the lowest Gibbs free energy per mole. Okay, and then you'll have these points of temperature where two phases will have the same chemical potential. And in fact, I haven't shown it on this plot, but you will get a point where there will be all three phases having the same chemical potential. That's that triple point. But in the case of two phases having the same chemical potential, as we saw in this figure here, right, we have coexistence. And those are the points where if you have two phases, the chemical potential of a molecule in either phase is going to be the same. Okay? And for a pure fluid, we see that we can get the melting point and the vaporization point through this analysis. Okay, looking at the triple point requires a little bit more of a complicated graph, so we'll use this approach. And it's not too difficult then to imagine that at the triple point, which is something that we really see, it's an actual thing, you'll have all three curves crossing at the same point, and that point would be the triple point for any pure fluid. Okay, so that allows us to say, all right, well, that's great. You know, we have this an explanation from thermodynamics, and for a pure fluid at constant pressure, we can go through these phases and these regions of coexistence, very special combinations, because of the fact that chemical potential at constant pressure is related to entropy. Okay, so any questions? Okay, so an important takeaway that I want to stress, okay, and this is something that, you know, is always good for multiple choice or, you know, these tables, right, is that at equilibrium, right, let's say you have a system that's in liquid vapor equilibrium, right, and here I've shown water, and you have the liquid and the vapor phases in equilibrium. I want to stress that the chemical potential of a molecule in either phase, and it could be mu H2O in the vapor, mu H2O in the liquid, these guys are going to be equal, okay? Because our system is the liquid plus vapor combination. That's our whole system, okay? So in this case, it's not just the liquid or the vapor or the interface or some part of each subsystem, but it's the whole thing, okay? And so if you were to have differences in chemical potential, if a molecule went from one phase to the other, then we wouldn't have a two-phase system, because the phase with the lower chemical potential would prevail, and the system would take on that phase, okay? And this is based on this concept that a system will find the minimum, a pure system will find the minimum chemical potential or free energy per mole. Okay. We can, so this is a liquid vapor system. We can look at something that's a solid liquid system. So this, in this case, you have a solid and liquid in equilibrium. Okay. Same thing. The chemical potential of water in the solid phase must equal the chemical potential of the liquid, of the water in the liquid phase. It has to be that way. Otherwise, you wouldn't see both at the same time. You would only see one or the other. Okay, and this is again at some combination of pressure and temperature, because we know that mu is the relevant thermodynamic potential that's associated with pressure and temperature being constant or being controlled. And so in this case, if you're on the ocean in your boat and you're under constant pressure because of your atmospheric pressure, and of course you can more or less accept the fact that the temperature will be constant, okay, for all intents and purposes. Though you may see temperature fluctuate as a function of depth of the ocean, or maybe there may be some gradients at the interface between liquid and air, but again, those are minutiae that detract from looking at the overall conceptual part. So any questions on that? Okay, great. So the next thing I want to address is this idea that of constraints. And so remember a couple of, well, maybe it was last lecture, I said that if you have a system that's in a single phase, okay, so let's say, going back to this diagram, let's say you have a phase point here. So you pick this combination of pressure and temperature, okay, you're in the solid phase of this pure substance, and in this case, it's water. But so if you wanted a pure phase, you have 2 degrees of freedom, meaning that you could specify pressure and temperature, okay? And you have a lot of you have a lot of combinations of pressure and temperature. That's what we mean by 2 independently variable intensive properties. Okay. Now you may say, well, yeah, it's kind of bounded by those curves, right? But yeah, of course. But if we were in the single phase region of the phase diagram, then you have a whole host of combinations of pressure and temperature that you can specify independently. Okay, and you'll still be having solid. The same goes for the liquid phase and the vapor phase. The interesting parts come in where you have these lines. Okay, and at that point, and on those lines or curves, you can only specify either a pressure or a temperature if you wish both phases to coexist. Okay, and so if you pick this temperature, let's say, right, and if you wanted to have liquid and vapor in equilibrium or coexisting, then your pressure would correspond, again, let's say this is T star, that's temperature of interest, where you want to see two phases in equilibrium. Well, then you follow the line up. It should be vertical, not slanted, but you get the point. And you see where it hits the curve where you would have coexistence with liquid and vapor. And then you would follow it to the left and find the pressure. Okay. So once you specify a temperature, the pressure is determined for you. You have no choice what that pressure is going to be. Okay. So what we say here is that you've lost 1 degree of freedom. So if you wanted a single phase, you have 2 degrees of freedom. That's temperature and pressure. If you wanted 2 phases in coexistence, either liquid vapor, solid vapor, or solid liquid, you lose a degree of freedom, meaning you can only specify either temperature or pressure. And then finally, for a pure fluid, in this part of the phase diagram, and this is water, right? Because it has that slant to the upper left, that makes water a very special fluid. Most fluids will have a slant to the right when you're looking at the solid liquid line, equilibrium line. So at this point, you have the triple point. Again, for this case, you have no degrees of freedom for a pure fluid. That point is determined for you. And then that, if you just think about it, if you sit down and you say, wow, that's pretty amazing, because that's something that we have no control over, right? It's pretty amazing that there are things obviously there are many things that we don't, in nature, that we don't have control over, but this is very simple. It's right here in front of you that point is determined for you. You have no degrees of freedom. Okay. So the thing I want to now address is, how can we quantify the number of degrees of freedom we have? Okay. So how many degrees of freedom do we have for a pure system? Or in fact, it can be a multi-component system, so it doesn't have to be pure system. How many degrees of freedom do we have given the number of components? So if you have multiple components and multiple phases, okay, how many degrees of freedom do we have? So that's the question I want to address now. So let me just, okay. All right, so let's see what we can do. So the question, so how many, what I'm going to call degrees of freedom, are available for multi-component, multi-phase systems. Okay. And so you have multiple components and you have multiple phases. And these are at equilibrium. Of course, everything we do here is at equilibrium. At equilibrium. Okay, so let's set up our little experimental system so that we can see what's going on. And the way we'll do this is to say that we have some system. Okay, it doesn't matter where it is. We're going to just subdivide our overall system into a whole bunch of phases. Okay, so just for simplicity, we can just show it this way. It doesn't mean that our system is like this, but it's just it's a cartoon. Okay, so we have phase 1 here. This is phase 2. This is phase 3. These could be any phases, right? Whatever they are, it doesn't really matter. And we're going to go all the way down to something, and we'll just call this the pith phase. So that's the Greek letter pi. So we have pi phases. Okay, so pi is equal to the number of phases in equilibrium. Okay, and a phase, right, though we know from a pure fluid is solid, liquid, and vapor, right? If you have multiple components, a phase can just be, you could have multiple phases that are all liquid, right? But they would each have different compositions. So a multi-phase system now has this added thing about composition. So a phase can have a different composition. And so even if everything is in the same phase in terms of solid, liquid, or gas, if it has different compositions, then those different compositions are enough to specify different phases. Okay? So all of these boxes, as I've shown here as phases, as representations of a phase, they could all be liquids, right? Of varying densities, perhaps. Okay, they could all be liquid phases. And the easiest one to think about is water and oil, right? If you have something if you have water and then it's in equilibrium with a very hydrophobic substance, you get this layering. And in fact, you could see maybe perhaps different fluids of different hydrophobicity layering one on top of, or different miscibilities with one another. So you would see this layering. And each of those layers would have a different composition. Right? And so composition is something that now distinguishes a phase. Okay. So we can have pi phases that are in equilibrium, and we're going to say that we have C number of components. So this is the number of chemical components or molecules, different types of molecules in your system. Okay. And we're going to say that these components can be present in all phases. So we're not going to discount the fact that some are not present in some phases. Everything is present. We make allowance for every component, every one of these C components to be present in every one of the pi phases. So any questions as I build this up? So as I build it up, ask questions if something is not clear. Okay. And then so each phase is going to have a temperature and pressure that is constant. So we have to say that temperature and pressure are going to be constant. Okay. So phase 1 will have a temperature 1, a pressure P1, and it's going to have compositions. Okay. We're going to say that for each one of these chemical components that we said are present in each one of these phases is going to have X11, which is the mole fraction of species 1 in phase 1. We're going to have X21, which is the mole fraction of species 2 in phase 1, all the way up to XC1, which is the mole fraction of component C, chemical component C in phase 1. Okay, and we'll have a similar thing for phase 2. We'll have T2, P2, and then we'll have X1, X2, 2, all the way up to XC in phase 2. And you can go down all the way to the pith phase. So is that clear? So that's our experimental setup. And so X sub I is equal to the X sub I J is equal to the mole fraction of species or component I in phase J. Okay, so that's just to be clear. And so now we're going to ask this question: how many degrees of freedom do we have? All right, so let's begin our analysis. Okay, so we said that we could remember from the very beginning of this class, and I've said this in the lecture today and last lecture, is that to completely specify a system, right, we need to have two independently variable properties that are intensive, okay, plus the amount. Okay, so that was one of the themes that we began with in our course. So in this case, we could carry that naively. So we can begin naively by considering temperature and pressure plus the compositions, okay, in the system. And so if you take this naively, let's see, we have pi phases, okay? We have pi phases, and so we can specify a temperature and a pressure for each one, just naively, okay? So naively, our degrees of freedom Okay, let's just start, is going to be 2 times pi. And so that 2 pi is the temperature and pressure for each phase. And that's sort of like what I've shown here with T sub 1, P sub 1, and T sub 2, P sub 2, all the way down to T sub pi, P sub pi. We could say that, right? So for each one of the pi phases, we have a temperature and pressure, so that's 2 pi. So naively, okay, let's begin naively. It's always a good place to begin. We have 2 pi degrees of freedom. I could specify a temperature and pressure for all of those phases. The other thing I can specify are the compositions. As I've just said, the mole fractions for each of the species in each of the phases, okay, naively. So I have pi phases and I have C species or C chemical components. So that would mean that I could specify pi times C mole fractions. Okay, so those are the mole fractions overall for the pi phases with C mole fractions in each phase. Okay, so that's naive. That's the naive way that we could say, oh, well, you know, if we had like 10 phases, right, pi is equal to 10, and we had 2 components, then we'd have what? 2 times 20 plus 40 degrees of freedom. You know, that's a lot. You know, you'd be like, wow, okay, that's a lot to choose from. That's a lot to manipulate. But in fact, it turns out that we don't have that many. So let's see what happens, okay? And we don't have that many because we have constraints. So it kind of makes sense, right? If you're talking about a degree of freedom, right? We have a lot of freedom. So naively, let's say in our example system, we have 40 degrees of freedom, 40 units of freedom. That's great, but now we have to introduce constraints. And so as your intuition tells you that if you have constraints, you're going to take away some freedoms, right? Like nowadays, right? Lockdown. Right? Lockdown is a constraint, and that constrains your freedom. So likewise, when we're talking about degrees of freedom in a system, constraints, okay, are going to reduce the number of degrees of freedom. Okay, it's a very simple concept. And those constraints come from thermodynamics. Thermodynamics and all of the analysis that we've done introduces those constraints. So in terms of the science, the constraints come from thermo. And in fact, they all can be traced back to first and second law. As you can tell from this course, the first and second laws are so important that you could, you know, all of the things that we're going to say. So these constraints that we've talked about are really just first and second law manifestations. So let's take a look at these constraints. Okay, let's take a look at these constraints. So what are the constraints? Okay, and let me, so what are the constraints? And keep in mind, and so this is important, each constraint reduces degree of freedom by 1. And so this is very important. Okay, this is, so as you identify constraints, you count all of the constraints that you have, okay, and one-to-one mapping for every constraint that you can find that's given by thermodynamics, i.e. the first and second laws, you're going to have to take away a degree of freedom, okay? So yeah, that's what thermo is going to do for us. So let's see what we can do. So the most obvious constraints, okay, are going to be related to temperature and pressure. So let's start those, okay? Let's start with those. And we know intuitively, and I didn't prove this to you, I could have proven this to you, but I'll upload this separately. Oh, by the way, I did upload the extensivity of G. Remember we said G can be written as the sum of mu I and I. So that's the latest file under modules. So if you want to see that proof, it's very simple and it's short and it's easy to follow. You can take a look at that file that I've uploaded as a PDF. So I haven't proven now the fact that for a multi-phase system with multiple components, okay, at equilibrium, the temperatures and pressures of all of the phases have to be the same. Okay, I haven't proven this to you. I will prove this independently and put it up as a file for you, okay? For those of you who really need to know and be convinced, okay? So we have constraints there that all of the temperatures, T1, T2, P1, P2, etc., all the way down to those for pi have to be equal, at equilibrium, okay? And you know this intuitively, right? Again, going back to the liquid vapor or the solid liquid ice water combination at equilibrium, you know that the temperature is not different in the two phases. That's one of the hallmarks you've been taught, that the temperature doesn't change when you have both of those at equilibrium. So at equilibrium, if you have multiple phases and with multiple components, all of the phases have to be at the same temperature and pressure. Okay, one cannot be different than the other. So in that case, our constraints, so the temperature and pressure constraints are written this way. Okay, let me just be clear. So we have T1 is equal to T2 is equal to T3 is equal to blah, 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 is equal to T pi. Okay, and so let's say pi is equal to 5. So we have T1 is equal to T2 is equal to T3 is equal to T4 is equal to T5. Okay, i.e. pi equal to 5. Okay, the number of constraints now that this introduces, right, is going to be 4. Okay, we have, this introduces 4 constraints. 4 constraints. And those 4 constraints are T1 is equal to T2, 4 unique constraints. Yeah. This is very important. 4 unique constraints. So that's, those will be T1 is equal to T2, T2 is equal to T3, T3 is equal to T4, and T4 is equal to T5. So these are the 4 unique constraints, okay? But you might say, well, what about T1 is equal to T3? Well, we can construct T1 is equal to T3 by saying that T1 is equal to T2 and T2 is equal to T3. So T1 must equal T3. This is the 0th law. Okay, so the unique constraints are that T1 is equal to T2, T2 is equal to T3, etc., etc. Okay? So any other constraint like T1 and T5, we can just build through using the 0th law, which says that if you have 2 systems that are in equilibrium, thermal equilibrium, i.e. having the same temperature as a third one, then those 2 would have to have the same temperature as well. That's the 0th law. Okay, that's the obvious one. It's intuitive. So what this means in the case of pi phases, if we have pi phases, this is for the case for, right, this is where pi equals 5, but in general, if you have pi phases, the number of unique constraints related to temperature are going to be pi minus 1. Okay, so this, in this case, we had pi is equal to 5. The unique constraints for temperature are 4. So it's going to be pi minus 1. Okay? And you can see that if you wanted to see that to an equation, it's the number of equal signs. So 1, 2, 3, 4. 4 equal signs means that we have 4 constraints, 4 unique constraints. Okay, so from the temperature then, we have pi minus 1 constraints. Okay, so these are the temperature constraints. So that means we've lost pi minus 1 degrees of freedom so far. Okay, so keep that in mind. We've lost pi minus 1. So that's temperature. The same thing is for pressure. We don't have to really worry too much about pressure because pressure, right, P1 is equal to P2 is equal to P3, yada, yada, yada. And that's going to be P sub 5, pi, okay, P pi. And so we know by analogy to temperature, you can think about this on your own because I think it's pretty straightforward and obvious. We will have pi minus 1 unique constraints. Unique being the operative word here, okay? So from the pressure, we'll have pi minus 1. So let me write that down. Pi minus 1 constraints from pressure. So from our naive discussion of how many degrees of freedom we have, which was this 2 pi, remember this was our naive, oops, let me write this down. This was our naive thinking about how many degrees of freedom we have, 2 pi plus pi c. From this total, we're going to now have to subtract at least a pi minus 1 number of constraints from the pressure and a pi minus 1 number of constraints from the temperature. Everyone follow so far?
Yes.
Great. Okay. Awesome. So now what we have to consider are any other constraints. Do we have any other constraints? And we do. Okay, we do. The first one, so let me see, that was capital 1. So let's go to so this is the next constraint or next set of constraints. Remember, for each phase, right, we have C chemical components. Okay. Chemical species, molecules, whatever you want to call them, they're unique chemical components in each species, in each phase. And so for each phase, X sub 1, okay, so this is for each phase. Let's say this is a jth phase. And so for each phase, so for the jth phase, X1 in phase J plus X2 in phase J plus X3 in phase J plus X sub C in phase J has to equal, since these are mole fractions, they all have to equal 1. Okay, and we can write this then, right? We already see here that there's one equal sign. So what this is for all species I in phase J, X sub I in phase J is going to equal 1. And you see here again, one equal sign for each phase. For each phase. That means we have one equal sign for each phase that arises from the chemical, the mole fractions being summing up to 1, right? Does that make sense, right? So we lose one constraint for each of the phases. We lose one constraint from each of the phases. Does that make sense? That means we can't specify one thing in each phase, and that is that one composition. So to make this more clear, maybe this is clear to you, okay? So example, right? If you have C equal to 2, then you're going to have X1 plus X2 is equal to 1. The mole fraction of 1 plus the mole fraction of 2 has to equal 1. You only have, so naively, remember, we said naively, going back to our naively, we said, oh, we have C components. We could naively specify the mole fractions of all C components in each phase. So that would give us pi times C mole fractions, naively. But we see here, right, very simply that for each phase, let's say this is phase J, right, the sum of the mole fractions has to equal 1. So if I specify the mole fraction of species 1 in phase J, I can't specify the mole fraction of species 2 in phase J. There's no way I can let one be 0.7 and the other one be 0.5. I can't do that. If I let one be 0.7, the other one is pretty much, I have no, my hands are tied. I can't do anything. Okay, it has to be 0.3. Okay, so for each phase then, okay, I'm going to have one constraint. And that one constraint, right, one equal sign, is the fact that the sum of all the mole fractions in each phase is going to have to equal 1. So because I have one equal sign for each phase, I have pi constraints that arise from mole fractions. Okay. Was that clear? So
as C increases, like you get pi minus 1 is associated with each increase of C.
You will get 1 for for each phase, you only have one, no. It doesn't matter how many components. For each phase, you will have one constraint that arises from this. For each phase, you have one constraint. So if you have pi phases, and sum of the xij is equal to 1 in each phase, how many constraints do you have? This box thing is one constraint per phase. And you have pi phases.
Yeah, pi constraints.
Pi constraints. So these are the mole fraction or composition constraint. Now, is that still not clear to you?
It's clear. Thank you.
No, if it's not, it's okay. I'm just asking.
It's
Here's
clear now.
Sorry?
It's clear now.
Okay, so here's two phase. Here's phase 1, here's phase 2, and I have two species. So x1 plus x1 in phase 1, x2 in phase 1 has to equal 1. X1 in phase 2 plus x2 in phase 2 has to equal 1. You see here that the mole fraction constraints is 1 per phase. So in this case, pi is equal to 2. So I would have two constraints. Okay? All right, I just want to make sure. That's all. So far from our naive discussion, we have to subtract pi coming from this, pi minus 1 coming from that, and pi minus 1 coming from that, okay? Just to keep things in mind. Now, finally, the last and most important, maybe not most important, but equally important, okay? Because we have things that can pass from one phase to the other, we have to deal with chemical potentials. And so this idea of chemical potentials, okay? Because each of the C components can be potentially in all of the pi phases, okay? They can go between phases, just like, you know, a molecule of water goes between the liquid and the vapor, solid and the liquid, yada, yada, yada. You can have any chemical species going from phase 1 up to into phase pi. Okay? They can be distributed. Of course, they would have different composition in each of the phases, and that's fine, right? But you can still have that. And of course, this is one way you could do separations, right? When you do separations, you might have a way of enhancing the composition of a particular species in one phase versus the other. So that's one of the fundamental conceptual ideas of separations. So because you can have C components in all the pi phases, we look at the chemical potential. So now we have constraints arising from chemical potential. See how important chemical potential is. We already know pressure, temperature, composition are important. Those are natural in our everyday language of chemical systems. But chemical potential is this thing that is now very, very important. And this is what we see here in an upper level course. So chemical potential constraints. Okay, G, this thing G, once again, rears its head. Okay, so we know, let's say, for each species, so we can take a particular species. Let's just do this explicitly. So let's say we have the chemical potential of species 1, okay, in, let's see, let me see how we want to do this. Okay, species 1 in phase 1, okay. What do we know? The chemical potential of species 1 in phase 1 has to equal the chemical potential of species 1 in phase 2. It has to equal the chemical potential in phase 3, so on and so forth, and it has to equal in phase pi. So for species 1, right? So what this is saying, and you can write this down, I won't write it down. What it's saying is that the chemical potential of species 1 is the same in all of pi phases. Okay. Okay. So how many equal signs are there? Anyone want to take a guess?
Pi minus 1.
Pi minus 1. Excellent. That's exactly right. Just like if you go back and look at the temperature and pressure, you'll see that it's a similar argument. So there's pi minus 1 constraints. So this guy gives me pi minus 1 constraints. Okay. So let's look at mu2. So let's look at the chemical potentials of species 2. So chemical potential of species 2 in phase 1 is equal to chemical potential of species 2 in phase 2, is the same as the chemical potential of species 2 in phase 3, and yada, yada, yada. And then we go all the way to, and so this is for species 2. And again, I don't think it's surprising that we will have pi minus 1 constraints. Okay. And so we keep going up to until we get to species C. So we can keep doing this now. And so we'll see here that the chemical potential of species C in phase 1 is equal to 2, is equal to its chemical potential in 3, and so on and so forth. So this is the chemical potential of species C in phase pi. Okay, and so we can just go down. And so this is going to be another pi minus 1 constraints. So now, if we add up all of these constraints, so each line gives me pi minus 1 constraints, okay? But how many lines are there?
C.
Very good, very good. Sheldon, yeah, that's right. So there's C lines, and each one of those lines gives me pi minus 1 constraints. So from the chemical potential point of view, because we know that all of the chemical potentials have to be the same in all of the phases for each species, right? The chemical potential related constraints add up to, we have pi minus 1 constraints, and we have C of them. So each row gives me pi minus 1 constraints, and I have C rows. So I multiply the two. And so that's how many constraints I have here. Okay, so again, this is from the mu I pi. Well, that's it. I think that's about it. So the temperature is all equal in all the phases. The pressure is equal. We took care of the composition and the chemical potentials. There really is nothing else at this point. There are no other constraints in the system. So all we have to do now is, from our naive discussion of the number of degrees of freedom, we just subtract out all of the constraints. And remember, for every constraint that we count, we subtract out a degree of freedom. So all we have to do is subtract out the number of constraints that we found in our discussion. So naively, we had, let's start with the naive number. We had 2 pi plus pi c. If we go back, where is that? Right, naively, we had 2 pi plus pi c. Now we just start subtracting. So let's go down and see what the first one is. All right, it's pi minus 1, pi minus 1. These are from the temperatures. Okay, so let's subtract those out. Minus pi minus 1, minus pi minus 1. So one is from the temperature, one is from the pressure. Okay, so let's go back and see what else we have. So here's the temperature one, here's the pressure one, we got those. Okay, this is from the composition right here. These are the composition constraints. So for each phase, we had 1. And since we have pi phases, that's pi. So let's subtract out a pi. And then finally, we had the chemical potential. So we've done this one. And finally, we have the chemical potential here. So we have to subtract out C times pi minus 1. Okay. So let's see what this leads us to. Can anyone do the algebra here? 2 pi. This will be the last concept for today. 2 pi plus pi c. Let's see, minus pi plus 1 minus pi plus 1 minus pi minus c pi plus c. Let's see what that gives us. So here's a pi c minus pi c. So here's a 2 pi minus 1 pi minus another, so that's gone. Let's see, these two are going to add up, 1 and 1. That's going to give me a 2. Let's see, here's a plus c still left over. And then here's a minus pi still left over. And then I think I got everything. So this is done, this is done, this is done, this is done. I got the 2 plus 1s. And I got the minus pi, and then I got the c. So now my degrees of freedom is this. In fact, it did turn out correctly. This is the famous Gibbs phase rule, which you see is not really a rule because we just derived it. Okay, that's why these things people like to call rules are really things that you can always derive from very fundamental things. I hate the word rules. Okay, so this degrees of freedom turns out to be 2 plus c minus pi. It's pretty amazing for a multi-component and multi-phase system. It's very general. Okay, it's amazing. Okay, and so let's go back. Okay, just as an example, and you know, I don't want to leave this for next class. I want to just finish it up here. Okay, so let's go back to water phase diagram. Here's our single phase system. Okay, so in this case, we're going to have pure water. Okay, our single component. So therefore, C is going to equal 1. Okay. So A, if pi is equal to 1, where you have a single phase, i.e. solid, liquid, or vapor, right? The degrees of freedom are going to be 2 plus C minus pi, which is equal to 2 plus 1 minus 1, that equals 2. Hey, wait a second, that's what we said before. So if you want to have solid water, right, you have 2 degrees of freedom. Any combination of temperature and pressure in the range is fine. That's awesome. So what about B? You want 2 phases, which is this coexistence. So we're going to have now pi equal to 2 phases, liquid, vapor, solid, liquid, solid, vapor. Again, C is just 1. We're talking about pure water because this is our example phase diagram that we're looking at. So the degrees of freedom is equal to 2 plus C minus pi, which is equal to 2 plus 1 minus 2, and that's equal to, wow, 1. And that's exactly what we said when we looked at the plot. If I want to have liquid and vapor in equilibrium at this temperature, I only have pressure given to me. I only have temperature. I set it. I said, I'm going to choose temperature. That's my degree of freedom. That's my 1 degree of freedom. And I'm done. And then finally, if you want triple point, where we have 3 phases, C again is just 1 because we have pure water. The degrees of freedom is equal to 2 plus C minus pi. And that's going to be 2 plus 1 minus 3 because pi is 3. And that gives us 3 minus 3. Wow. No degrees of freedom. Everything is chosen for me. Amazing. Amazing, amazing, amazing. Okay, so this idea of the constraints, removing our degrees of freedom is a very powerful one. Okay, and so this is embodied in this thing called the Gibbs phase rule, which is really not a rule because you see that we just derived it from a very careful analysis using the results and the tools from first and second laws of thermodynamics. Okay, these kinds of things really get me excited. It's pretty amazing that this happens. And so we're going to use this. Okay, so this Gibbs phase rule tells us something about pure systems. Okay, um, now we're going to move into binary systems when we get back from a break. Okay, we're going to move into binary systems where we have two components. Okay? And that's going to just make things even more complex. I mean, you'll be surprised just adding one more species, what that does. But it's nothing that you should be afraid of. But what I'm saying is it's going to allow us to get something more rich, a richer phase diagrams and what have you, and some very interesting science and chemistry and physics behind it. So any questions on this Gibbs phase rule? And I hope that I convinced you now that quantitatively we can get this thing called degrees of freedom, and it matches, okay, this science, this thermodynamics actually recapitulates what we see in nature. Okay, and that's very comforting that it does that. It's very comforting. And it should, right? It's been around for centuries. But any questions or comments for discussion? Okay. Well, I appreciate everyone's participation. I wish everyone a really great break. I hope everyone's safe and stay happy. Get outside. Great weather this weekend, and we will have the exam graded for you and so on. Okay. So thank you all for your